please go ahead.
So thank you, Dr. Danish, for getting me along. And first of all, I would like to welcome Dr. Vivek Kumar Agarwal on the behalf of Department of Civil Engineering. Dr. Agarwal is currently working as assistant professor in Delhi Technical University. He has completed his MSc Applied Mathematics from IIT Roorkee and acquired PhD degree in mathematics from IIT Kanpur. Dr. Agarwal will be delivering a technical lecture on introduction to MATLAB and its application to least square method for data science. So over to you, Dr. Agarwal.
Yeah, thank you, Dr. Jayed Mohammed. And first of all, I would like to thank Mohammed Danish for inviting me for this faculty development program on the advanced MATLAB for scientific computing. So today I will going to talk about the least square method. Now these days everyone is talking about data science. So whenever you have a data, but just before that I will share my slides. Yeah, is that visible to everyone?
Yes,
Yes.
Okay, so I will like to thank the Dr. Danish and all the organizing team for giving me this opportunity to talk about the least square method in the FDP. So why actually the question is that why I have chosen this methods, the least square method, because I just want to talk about these days we are talking a lot about the data science, and in the data may be a sparse data and it's a big data. So somebody asked me that how you can do the approximation that whether this data can be captured with a line or with a quadratic or with any function. So how you can do that? So the best method these days we can deal with is the least square method, because its name is least square because it minimizes the error between the data values and the approximate values. So everyone knows that this belongs to the curve fitting. So curve fitting, also known as the regression analysis, and is used to find the best fit line or the curves for a series of data points. So I think the audience, the participants are familiar with this type of things. What do you feel?
Yes, we have participants from different fields. So I think many of the participants must be aware about the curve fitting.
Okay.
And the mic of participants are muted, so they will not be able to speak unless I. So.
Okay. So I will.
But I request participants to write your questions in the chat box. They can write it. I will unmute them.
Okay.
I think Dr. Vivek, just a little bit of background for these applications that you're going to discuss over here. For our audience, those are not from the background. That would be better.
Yeah, so background is this, that suppose as a civil engineer, suppose you are taking, you are measuring something and you are taking again and again the values by measuring some structure or something. So that values is the approximate value, right? And then if you collect all these values, then you want to find that, okay, so suppose you every day you are taking some value or every hour you are taking some value. And now somebody asked me that, okay, you have taken the values at 3 o'clock, then 4 o'clock, then 5 o'clock, like this one, then what is the approximate value at 3 o'clock? 3.5 minutes, means 3 hours and 30 minutes. What is the value of that one? Or maybe you are unable to take the value in between some point of time from the for the interval of time, then you want to approximate that value. So in that case, you have to take the help of mathematics, and that is also known as interpolation, because you have the data points and you want to approximate a function to this data point, and later on using this function you want to do some prediction, like you are calculating that the weather, the temperature of a day at suppose every half an hour, and based on this temperature, suppose yesterday it was the 14th September, so you have taken the values of the temperature at every half an hour, and based on that values, now you want to predict the weather of tomorrow. Tomorrow means today weather, 15th September. So in that case, you will collect the data, and data will be very big data. So based on this data, you are going to predict the future. The question is that how you are going to predict the future. So whatever the data you have, you will try to fit a curve that is the best fit curve to all these data points. So once you know this the curve, then you put the value of, suppose you want to calculate the value of tomorrow, then you put the value of that time t in that one, and that gives you the prediction. So basically the data is corresponding to the observation you are collecting, and then using this observation you want to do the predictions. So that is the basically the point of view of the scientific computing. So I think now it is clear that what is the background of this one. So the question is that you have the data, and then how you can use this data for the prediction. So there are three type of curves fitting methods. So these methods, if you see, I will use this also. Now, so this is the three type of methods are there. So the first method is the method of least square. Another one is the linear interpolation, and then you have also, I think, sometimes you came across the word splines or the curvilinear interpolations. So this is the way we can do. Now suppose so this is a curves. Now suppose this is the points I'm talking about. So suppose this is your data point. One data point, 2, 3, 4, 5. So 5 data points are there. Now using this data point, I want that what will be the curve fit that is going close to all this point. So this is called the least square method. Now based on this one, you can see that this line is passing through only 3 points, 1, 2, 3, and it is not passing through these 2 points, but still it is called the best approximation, that is the least square approximation. So that we will discuss that why it is called the best approximation. Another one is that the linear interpolation. It means that what we are doing here is the same data points are there. Now using these data points, I will approximate the function from this point to this point linearly by line, then again by line, and this is my line, another line. So in this case, what we are doing is that we are approximating the data with the linear curves, and you can see from here that it is passing through all these points. So everything is passing through all these points. So this is called the linear interpolation. Then we come across the another interpolation, and that is called the splines or the non-linear interpolation, because in both the cases we are approximating by the line, but here we are approximating with a non-linear function. It means that is not the line. So what we are doing here, we are using the spline functions here. So spline means that it is not a linear function and it is passing through all this point. So sometimes we use quadratic spline. Sometimes we use cubic spline. So this type of spline we use for the interpolation. Cubic spline we are taking because that will give you a smooth function. Quadratic spline also gives you the better approximation. But linear interpolation, if you see, then it is just the continuous function and not differentiable. But here, if you see, it is a smooth function, it is a differentiable function. So cubic splines, quadratic splines. So splines plays a very important role in data science or whenever we are going to approximate the given data points. But here it is a linear interpolation and this is the least square method. Now, so in this talk, we'll cover the least square approximation, that how we can do the least square approximation. We'll discuss about the normal equation and the type of least square curves fit. Fit means that we are going to fit in the given data. Then we'll discuss some MATLAB examples, that how we can define the straight line fit, how we can do the parabola fit. And then we'll discuss the pros and cons and the application of the least square method. So basically, what are the least square? The least square, as I told you, the name is say the least square. So it minimizes the square of the error between the original data points and the value predicted by the normal equation. So this is give you the minimum of all the errors. That's why it is called the least square. Least, we have the error, taking the square of that one and finding the least value. So the name comes from there. So that is the least square method. Further, the method of least squares allow us to describe a model as being represented by the line of best fit. So this is also called, the least square is also called the best fit. Because why it is called the best fit? Because in this case we are minimizing the error. So error is there. Now, how to ensure the best fit line? So the best fit line, if you see, so the best square regression line. So if you go to the statistics, there this type of line is called the regression line. So that's why the word is coming. So the least square regression method, the best line is one that minimize the sum of the squared vertical differences between the points and the line. So that is, will tell you that what is the meaning of this one. The smaller the sum of the squared differences, the better the fit of the lines to the data. So because we are taking the smaller of that one, so if the error will be the smaller, the better will be the data, fit of the line to the data. So that is the mathematics behind this least square method. So this is the geometrical point of view. You see, suppose you are doing something and you have collected some data. Now, after the collection of the data, you put the data point in your graph. Suppose you are using MATLAB or any other, and you plot that data point in the graph. So suppose I plot this one, and this is my data points I got here. So these points are, if you see, they are not lying in a line or in a quadratic or in a cubic form. This is just the random data points you have collected, and this is not follow any particular function. It is just, so this type of data is called the sparse data, and this is spreading, already spreaded over the domain, this one. Now somebody asked me, okay, this is the sparse data, and I want to fit a curve that represent these data points. So if you see from here, then suppose my data point like this one, only suppose I have this type of data points like this, 4 data points suppose I take, and somebody asked me that what is the best curve which is going close to all these points. So I will say definitely a line. I will take a line, and this is the passing through all these points. So this is, so I can approximate a curve using these data points. So this is, I can take as the best fit. But suppose my data points are not linear, it is something like in this form. And if somebody asks me that now what is the best fit curve for this one, so if you see from here, I can take a curve passing all these points like this one. And if you see from here, it is, I can say it is a type of quadratic curve. So it is type of quadratic curves, like you know, it is a parabolic form. But here, if you see, then you have a sparse data, and you are unable to think about any curve which is going close to all these points. So then what we'll do, what the mathematics people started doing is that suppose we want to put the best fit line from this data. So what is the meaning of this best fit line? Now what do you do? That suppose I take this line and I call this y is equal to, suppose, a0 plus a1x, because this is the equation of a line, and in the line we need only 2 parameter, a0 and a1, to find out the value, to find out the equation of the line. Now I take that, okay, this is the line, is the best fit line. Now what I do is that if you see from here, I will start collecting the error. So my error is, suppose I take E1. So E1 is my, suppose I take this data point. So this data point, I like this one, X1, Y1. Second point is for this, X2, Y2. Third point is this, X3, Y3, like this one. So points are there. And this line is, I call it capital Y. Now my error is Y1 minus capital Y. So this small y1 is the value of this star, and this capital Y1 is value coming from this line after substituting this value. So if you see, E2 will be Y2 minus Y2. So it means, if you see, this is the error coming from here. This is the error coming from here. Now this is the error. Okay, so this is the error. Like this one, I calculate all this error, and I call this error, this is my E2, this is my E3, this is E4, E5, like this. So what I do is that I collect all the error. Okay, so this is what I told you. So this is what we are doing. So I will collect all this error, and I call this EI. Okay, so EI is, as I showed you here, that because my data point we are taken in this form. So this is my line, b is equal to x. So this is the line I'm taking from here, and these values are already given to me. So you can take this as yi minus capital Y. Because if you see from here, this is equal to B. Whatever the form, we just taking the line. Y, you can write as a Y. Now, all this error I'm taking, now I take this error, now this error, and what I'll do is that I will take the sum of this error. Now, the word is least square method. So what I'm doing, I will take square of all this error, taking the summation, and then I will take least of this value. So that is because this error is this one, I'm taking the square of that errors, and then I'm putting the least. So least means we have to minimize. So minimization is the optimization process, and we already know in, so the students who are not familiar, they can remember that in their +2 level in mathematics, we need to find out the maximum value of a function, minimum value of a function. So that is called the minimization and the maximization. So here our main target is that whatever the error we are getting, that error should be minimized. So this is what we want to do. So that's why this word least square comes from. So this is what we are doing here. Now we have taken the error, and then I'm taking the square of that. Somebody can ask me that, okay, why we need the square? We can also take like this summation I minus aix. So I can take this value, but you know that this value can be positive or negative. So if I take the summation, you may say that this value becomes 0. And in that case, you will say, oh, error is 0, so it is the best approximation. But ultimately, what is happening? Like here, suppose this is my some error E. I can have a similar error in the downward direction, and that will be minus E. And if I add E plus minus E, then the error will be 0. So in that case, this will be 0. So that's why we cannot take this value, not possible. Then somebody can ask me, okay, you are not taking this value. You can take like this, EI minus AIX. So this is just I taken the modulus value, just to get rid of this negative sign. But in this case, if you see, and if you remember mathematically, then you must have seen that the function x modulus value. So this function is not differentiable function at x equal to 0. So this function is not differentiable, and later I need to find out the least value, the minimized value, and minimization, maximization. If you remember, that needs these derivatives, because if you remember that finding the maximum value of function or the minimum value of a function, we need to take the derivative of the function. So in that case, we are unable to take the derivative. So we also remove this possibility that, okay, we cannot take this one. But this is okay because it is a square function, and I know that I can take the derivative of this function very easily. It is a smooth function. We can differentiate very easily this function. So that's why we are taking this value square. So this is how it is different from the interpolation. So interpolation, if you remember, interpolation word is meaning that approximating a value of a function between the two given values. So that is called the interpolation. Like suppose you take this, I just Suppose you have some data like this one, like this. So you have 4 data points, and the interpolation is passing through this point. So I suppose I approximate this by the cubic function. Now interpolation means somebody asked me what is the value of the function at some point here, maybe some point here, or maybe some point here. So I'm approximating the value of the function in between the given values. I'm not going away from this. This is my boundary. So I'm not approximating any values beyond these values. So that is called the interpolation. If somebody wants to approximate the values outside this, so that value is called extrapolation. So unlike interpolation method, the method of least square, we fit a polynomial or some other functions which may or may not pass through any of the data points. So that is the biggest difference. Because if you see from here, this curve is passing through all these points. But if you see the least square method, this line is hardly passing through any point. It is passing through only, if you see one point here, approximately this is also passing through this point. That's it. And one point is also. Otherwise, it is not passing through more than maybe 3 points. And still we are calling it the best fit. So that is amazing thing. Now, this is called the least square approach since the square of the error is minimized. So that's why it is called the least square approach. Now the question comes that how it works. Now the main thing is that how we can find out the value of this linear fit. Because in this case we are fitting by a line. So how we can do that? So now let's take that how we can do. So suppose I have data points, as I told you, that these data points you have, and it is given you in the form of x1. So these data points you always collect in terms of x1, y1, x2, y2, and suppose I take n number of points. So it is always given you in this form. So this is the data points you have collected from the observation. Suppose you are taking some readings of something, and then based on that reading, you have collected this data. That's it. So it is just a reading you are taking. So this is I have in hand. So that is called the data. Whatever you are doing these days, so you do the calculation, you take the readings and whatever you are doing. So in that case, you will collect the data. So this data is given to me. That's it. Where? So it is written that let xi and yi be given data where some values of xi of the variable x, the value of the variable y is given as yi. So this value is given to me. Now, in the least square method, ordering sequencing of nodal point is not essential. It means that in the least square, first suppose you are doing some observations, taking some readings. So first you have taken this reading, then you have taken this reading, then you have taken this reading, and in the last you have taken this reading. So that is called the ordering. But when you are putting this data, using this data, somebody use this data first, somebody use this data, and then use this data, and then use this data, and then use this data. So it is saying that it is immaterial. So in the least square method, ordering and sequencing of the nodal point is not essential. So this nodal point is meaning that the value of this xi. So these are called the nodal values. So this is the ordering is not needed as it is needed in the interpolation. The second one is in the method, we can approximate the given function may or may not be known. So that is a big thing, that the function may or may not be known. by a polynomial or some other standard function. Why we want to approximate the function with a polynomial? Because everyone understands the polynomial, and polynomial is the easiest function we can deal with. And other thing is that the polynomials, I know, is very easy to deal with in the terms of derivatives. You can easily take the derivative. You can easily take the integration of that function. So that's why we always want to approximate the data with a polynomial or some standard function like a trigonometric function or exponential function like this one. Now, least square approximation estimates a best fit solution for a system by minimizing the magnitude of the resulting error term. So we are minimizing this one. That's why the word least is there. We will discuss the linear least square regression in this presentation. So I will talk about only the linear form. The same works for the non-linear also. So this is what we are doing here. The linear least square regression. The linear least square regression is the simplest example of the least square approximation, that is a fitting a straight line to a set of paired observations. So whatever the observation you have collected, you put this observation like this one, and now you approximate this one by the straight line. So this is the straight line. Y is equal to a0 plus a1x plus the error term. So error term I told you. So that what is the error here? If you see from here, the error will be y minus this a0 plus a1x. That will be my error. So this yi's are given to me here. So what I do is that suppose I take y1. So y1 is means this value, and I put this x1 here in this line. So whatever the value is coming, a0 plus a1 x1. So now I will put the value of the x coordinate here and find the value with the line. And this y1 is already given to me. So the difference between these two is I will take. So this is the error term or the residual term. And I can find out this error terms for each and every data points that is given to me. Now, how to compute the a0 and a1? Because if you see from here, if I approximate the function with this line, then I need to find what is my a0 and what is my a1. And if I able to find this one, then I'm done. So how we can do that? So it is written that one way is to use optimization techniques, since looking for the minimum, right? That is taking the derivative, and then from derivative we'll find out the critical points, and then we'll find the minimum. Another way is to solve normal equations and to find the value of the coefficient a0 and a1. So this is what we are going to do. We'll discuss that what is the normal equation also. Now, derivation for the normal equation. So what are we doing? What we are doing here? We have calculated this error. So if you see, this is my I. So EI we have calculated, taking the square. So I will call this as summation I from 1 to n EI square. So that is my summation. First, now we'll do this one is no, this is summation, and this is a partial derivative. So what I do in there, now I need to find the value of a0 and a1. So, and I want to do the minimization of this one. So now you can say that this is your cost function. and you want to minimize this cost function based on the values of a0 and a1. So this is the only two things you can find out the value of this parameter. So what I do is that I will differentiate this with respect to a0 and with respect to a1. So this is the partial derivative I'm taking with respect to a0. First I will take. So what I do, I will take 2 times into this function into -1. So that's why -1 summation this value. Here also with respect to a1, so -2 will come there, because if you take the derivative of this function, yi minus a0 minus a1 xi square, and if I want to differentiate this one, so suppose I want to differentiate with respect to a0, what will you do? I will take 2 here, then y0 minus a0, sorry, yi minus a1 xi into the coefficient of a0, this is -1. So it will be -2 and this value. And summation will be there, no problem. Now I'm taking with respect to a1. So this is also summation. This is partial derivative. Now I'm taking with respect to a1. So in this case, everything will be same. Only the coefficient of a1 will come, and that is my xi. So that's why this xi is coming. So -2 this and minus xi. Now what I will do, I will take the partial derivative and I will put this partial derivative equal to 0. See, so this yeah, this is the. Now what we are doing here is I will take this partial derivative and putting this equal to 0. This is my first equation and this is my second equation. And now if I take these values and taking this summation inside, now if you see the summation will be summation yi is the first value I have taken minus 2 into this. So I'm taking this value. So summation ai x, so that will be equal to 0. In this case, I will take this xi inside and multiply by each term. Then it will be yi xi minus a0 xi minus a1 xi square, and putting this equal to 0. So now I will get these two equations, and I need to find the two values, the two parameters, a0 and a1. So I need two equations and I get these values. Now I can solve these equations. So if you see from here, this equation, if you take on this point values, because this value is known to me. Now I will take this value. This value is also known to me. So I will calculate this value, and this a0, if you see the summation I am taking from I from 1 to n. Everywhere I am taking the summation from 1 to n. So if I add this a0 n times, then its value will be n into a0. So it is here. Then I'm adding this one, so it will be summation xi. A1 is a constant value, and that becomes equal to summation of yi. So I'm taking this value and putting this on the left hand side. So I get the first equation. In the second equation also, a1 is there, a0 is there. So a0 I will take out, and this is the summation, this is the summation, and that becomes equal to summation of xi yi. So now this is called the normal equation. Now we are going to solve this normal equation to find out the values of a0 and a1. Now if you see from here, this is my matrix, and this is my right hand side. So now from here, if you see, I get my A. If I take this matrix as A matrix, okay, and suppose I take this as X, so, and this as, suppose I take by B, so I get the system of equation like this form: Ax equal to B. Now the question is that how I can solve this system of equation. Now, if you see from here, this is a 2 cross 2 matrix. So it is 2 cross 2 matrix. Now, if you also see from here that this value and this value is same, it means this matrix A is a symmetric matrix. Okay, so it is a symmetric matrix and it is a 2 cross 2 matrix. Now the question comes that can I solve this by taking the inverse? So I can solve this by writing A inverse B. The only question comes here that can I take the matrix A, which is invertible matrix? So this matrix is coming from here. The question is that whether the matrix A is invertible or not. Because if this matrix is invertible, then I can take the inverse of this and I can solve this one. And that will be the solution. But if the matrix is not invertible, then what I can do for this? So this things is the big question in terms of mathematics, that now you have to prove that this matrix is an invertible matrix, and only then you are able to solve this equation. And suppose I solve this equation, then the value of A1 is coming this and A0 is coming this. So this is the types of least square curve fit. Now, first of all, I just want to tell you that how we can be sure that this matrix is an invertible matrix, so that I am able to solve this matrix. So let's say do that one. So this is little bit some tricky is there, and for that one we need some type of linear algebra. Now we have the data points. So if you see from here, I have a line that is my A0 plus A1x, and I want to find the value of A0 and A1, and I have the data points, that is my x1, y1, xn, yn. So I put the value of x1 here and I get the value of y1, whatever the y1 is coming from there. So what I do is that, if you see, I can write this as a matrix. And here I can write A0 and A1. If you see from A, the coefficient of A0 is 1 and coefficient of A1 is x1 when I put the first element. Then I put the second element. And like this one, I keep putting my all this point. And on the right hand side, I will get the values of yi. This is y1, y2, and yn. Because first I will consider that let this line is passing through all this point. And if it is passing through all this point, then definitely if I put the xi, it should be equal to yi. So this is my equation basically we are getting. And if you see from here, then this matrix will be of dimension n cross 2. And this is dimension is 2 cross 1. And this is also n cross 1. Now this is the matrix. In fact, this is not a square matrix. So I can call this as some A value, I now call it A, and then I will call it X, and this is some B. This I write like this one, this matrix. And if you see from here, then this matrix is not a square matrix. Now, if the matrix is not a square matrix, then how we can solve this one? So I think you already know that matrix is not a square matrix. Then we can make this square matrix. And how we can make this square matrix? This is the way we can do that. Ax is equal to b. Now what I do is that I will just take the transpose of A and multiply both sides. This is the transpose of the matrix. Now, if you see from here, then I get a matrix A transpose A. And what is this A transpose A matrix? So A transpose will be dimension 2 cross n, and A is n cross 2. So it means that A transpose A, the matrix will be 2 cross 2. So it will be a 2 cross 2 matrix. Also, the matrix A transpose A is symmetric matrix. So this is how it is symmetric, because I'm taking the transpose of this one. So it is A transpose and A transpose transpose. So that is A transpose. So it is a symmetric matrix. Now, if you have a symmetric matrix, it is a and also one thing, just keep in mind that this is a also positive definite. So it is a positive definite matrix, and now based on the, I'm not going to give the detail. So this matrix is, in this case, is invertible. But the question is that what is this A transpose A? Because whether I'm getting this same matrix here or not, that is the questions. Because I need to solve this equation. This is my normal equation, and I have to solve this equation. But I'm dealing with these things now. Now what I do is that, let's see what is going to happen. So this is my matrix A, I'm calling here. Now, if I take transpose of this matrix, just try to understand that we're taking the transpose of this matrix. So it will be 1, 1, n times, and this is x1, x2, xn. And this one my matrix 1, 1, 1, 1, and this is x1, x2, xn. Now, if you multiply this, see that you get like this one. Multiplying this column with this row, so it is n times, so it will be n. Now multiplying this column with the first row, so it is the summation of xi's. Multiplying this column with the second row, so it will be summation of xi's. And multiplying this, the last column with the second row, so it is xi square. So we got this value multiplying. And if you see from the above, this is the same as this matrix. You see, same value we're getting, whether I'm taking A transpose A or I'm getting this value. So you see from here that you are getting the same values here. Because I wanted to discuss whether this matrix is invertible or not. That's why I'm doing this one. And I found that A transpose A is the same matrix as we are getting from the taking the partial derivative equal to 0. So it means I'm getting the same value here. Now, using this one, I came to know that because its rank is 2, so this matrix is invertible. Is invertible. Now on the right hand side, if you see, right hand side will be this value. So if I take this in my y, this is I have taken here. Now if I take the transpose 1, 1, 1, 1, and this is x1, x2, xn, and multiply by this y1, y2, yn on the right hand side. So if you see from here, you will get this value. Taking the column with this first row, so it is a summation yi's, and taking this with the second row, it is a summation xi's yi. So right hand side value is this value, and this is the same as this value. See, the right hand side is this value. Basically, the way we have taken the partial derivative and the way we are taking the help of matrix analysis, we are getting the same system. So using this system, now I should be able to solve, because I found that this matrix is invertible matrix. So I can solve this system of equation to find the value of A0 and A1. Okay, so this is the linear fit. So this is the equation A0. So you can call it M0 is the A0 basically, and this is my A1, and then we can find out the value. Now, polynomial fit. So in the polynomial fit, see, we have the way we have calculated. I will show you in the MATLAB that how we can find out the value of A0 and A1 for the given data. Now, I can use the same things with the quadratic or with the cubic. So this is the methods tells you that, okay, least square I'm using not for the linear fit, but the polynomial. So in this case, I take the polynomial as a y is equal to m0 plus m1x plus m2x square up to x. So this is the polynomial of degree k. Now, why are we doing this one? Just because we found that this line is not passing through any point, and we maybe want the higher dimension. So in that case, we are going to approximate the best fit with this quadratic function or the k degree polynomial. So the more complex the curvature of the data, the higher the polynomial order required to fit it. There is no data restriction associated with this curve fit. So that is also there. For example, now for a function that are nonlinear in the parameters fitting a Gaussian function. So this is the Gaussian curve function. So in this case, if you see from here, I need the value of a, b, and c just to approximate the given function with the Gaussian function or with the sine function. In this case also, I need the value of a, b, and c. So three equations are needed to find out this value. So there is an important class of function that are nonlinear in parameter. This is nonlinear in parameter means here if you take the square, it means you get the square of b or c. So that becomes the parameter becomes nonlinear, but can be linearized in the form of coefficient. I can linearize this one with the help of Taylor expansion or maybe log function. So this, whenever we deal with, we can linearize this function, and then we can use this for linear fit. For example, exponential, logarithmic, or power function. So I can linearize. This is a sine function. I can take it sine series and then approximate with the linear form only. So least square curve fits. Suppose I take the exponential function. Now in this exponential function, I need to find the value of m0 and m1. So what I do is that I just take the log of this value. And you will see that if I take the log of this value, it becomes like an equation, line. Right? Because if you know, then I just take log y is equal to log m0 e m1x. So this one I can write. And now I can write this as a log m0 plus log e m1x. And exponential, so if you see from here, it will become log m0 plus, so I can write this as a m1x. And that is my log 1. So if you see, it become a linear function. Now I consider that let I write my log y as capital Y. So from here, I just take log m0 as m0. Then I can write this as a capital Y is equal to m0 plus m1. And if you see, this is becoming a linear fit, a linear equation. So this is the way we can use different curves, and then we can use that as a, so it is generally used to fit data that, so because it is an exponential function, and now suppose your data is like this one. If you take your data and suppose your data is like this one, like this one. So this is your data. And if you see from here, you will consider, oh, okay, this data looks like this one. So why not we approximate with the exponential function? So that is the way we are taking it. So it is said that it is generally used to fit data that increases or decreases at a higher rate. So this curve fit cannot be fit negative because we know that the exponential function is never negative data or data equal to 0. Not on the semi-log plot with the linear x-axis, the curve appears as a straight line because here we are taking the log values. So if I take the log semi-log plot in the MATLAB, then it will look like a linear plot. Again, the same thing we do with the logarithmic fit. So this function fit a curve through the data of the form this. So y is equal to m0 plus m1 log x. So a value is given in the terms of log. This x coordinate is given to you in the terms of log. So a logarithmic curves fit a generally used with data that span decade in which the value of x is very big. Suppose the value of x is like 100, 101, or you are calculating some values at every century. So you have calculated some maybe the change in weather in the century. So what you are doing, first you have calculated the weather at 100 years, then maybe next you can use as a 200 years, then 300 years, then 400 years. So in that case, the value of x is very big. So in that case, if you want to approximate, then we'll take the log x so that we can make these values approximately equal to y. So because x is a very big number, so we can take the log x just to make it the comparable to the y. So this curve fit cannot be used to fit negative data or data equal to 0. And whenever we do here, so we'll take, suppose we take the semi-log plot for the y, then it look like a straight line. Okay, so this is the different type of fit I'm talking about, and this is the next one is the power fit. So power fit means I take a function in the power of x. So I have the values here m0 and m1. Two parameters are needed, and I'm considering that let y is equal to this one. So in this case, if I take m0 is maybe 1 and m1 I take 2, so you'll see that y is equal to x squared or x cubed or x4. Now these days people are using fractional fit. So fractional fit means I am considering maybe this value with m0 x 1 by 3. This is the fractional power we are taking. So in this case, this is part of the power fit. So this curve fit cannot be used for negative data or data equal to 0. And in this case, we'll take the log plot. Then the curves will look like a straight line. Now we can do these things in MATLAB. So I hope that the students are familiar with the MATLAB. Now in the MATLAB, you know that how to find the polynomial, how we can write the polynomial. So this is the basically the polynomials how we can use in the MATLAB. So many functions can be well described by high order polynomial. So in the MATLAB, what we do is that this is suppose third degree polynomial, and like this one, if I calculate p is equal to 1, 0, minus 1, it shows that it is a polynomial of degree x square. The coefficient of x is 0 and constant term is minus 1. So it is x square minus 1. It is 29x cubed. So if I write this polynomial in MATLAB, this polynomial is represented by this one. So it is basically gives the coefficients of the polynomial. And we can use these commands to find out the roots of the polynomial, or I can evaluate the value of the polynomial for given x. This is the way we can find out. And this is the command we are going to use many times is the polynomial fit. And this n is the dimension, the degree of n. If I put 1 here, it means it will give you the polyfit of the given data. So x and y are the given data. So it will, if I put n is equal to 1, so let I write p1. So p1, suppose I write polyfit x, y, 1. If I put x, y, 1, it means I am considering the linear fit. If I take 2 here, so write p2 is equal to polyfit x, y, 2. So it is giving you the quadratic fit like this. So this is, so do a least square fit with a polynomial of degree n. X and y are the data vectors and a is coefficient of the polynomial. So this is the way we can deal with this. Now I will do this one in MATLAB. So let's take the given data in this form. Suppose my x is there. So this, suppose you have the point -1, 0, 0, 0, minus 1, 2, 3. So this is the data points you have. Now, if I put the x, y, 2, it means using this point values, I'm going to have the second order polynomial, that is a quadratic fit. So this type of things you can use with MATLAB. So I will show you this one. I will show you that how now we can use MATLAB. I will remove this one. Now, so this is the MATLAB. Yeah, so this is MATLAB. I hope this is visible.
Yes, sir, it's visible.
Okay. So just here. So this is the MATLAB. You can see from here that it is 2020. Latest MATLAB we are using here. Now I will tell you that how we can use these least square methods to approximate the given fit. So first of all, that I take this value. So first I will take the data points. Okay, so I will just take x and I take the data point. So suppose I take data point 0.8, maybe I will take, then maybe I will take 1.4, 2.07. So this is just x I am taking, 3.8, 4.8, 4.9. So this is the, suppose I'm taking 6 values. So this is my x coordinate I'm taking. Then I take the value of y. So this way we can put the values of coordinates in the MATLAB. So it is, suppose I take 0.69, then 1, then 2.02, then 2.39, 2.34, and 2.83. So this is the value of x and y I have taken. Now, so this is your data. You can take different type of data, but suppose this is my data. And now somebody says that, okay, you make the least square fit or the quadratic fit for this given data. Now, if you see, I can plot this data. Plot this x, y, x, y, and I just plot by maybe with a black color. And this is my plot. Are you able to see this plot?
Yes, sir.
Yeah, okay. So this is, you see, you can see that this is my first data point. One is here. Then it is the second data point. This is there. Third is here. Fourth is here. And like this one. Fifth is here. And sixth is here. Now you can see from here that these data points are just spread over the XY domain. They are not in the straight line, or they are not following any path like a quadratic or a cubic. So it is just a random data I have taken. Okay, so this is the way we can plot the given data. Now I want to use that, okay, after doing this one, now I want to fit the linear. So I will tell you by the inbuilt command of the MATLAB, and also I will tell you that how we can find out the value of A0 and A1, because if you see, then we have chosen the y is equal to A0 plus A1x. Okay, so this one will do that how we can find out. So if you remember, I will take the matrix A, and that matrix, it was first value was 1, and then it was the x1. So x1 is basically, I will write x1 because this is my x. So x1 is 0.8. Then I will take 1, and then I take x2. Then I take 1, and then x3. Then I choose 1 because first column was 1, 1. That's why I have to take 1. Then x4. Of course, I need to take again 1, and then x5, then 1, x6. So suppose I stop here, and that is my matrix A. So this is my matrix. First column is 1, 1, 1, and the second column is the values of the x coordinates. That is there. And then, if you remember, then on the right hand side, I need the vector B. So B I just take again because Y is there. So I will just take the B as Y dash. Y dash means this Y was a row vector. I will take the dash, it will be the column vector. So this is my right hand side vector. And I know that I need to solve this one. So I will first I need to find the A transpose. So the A transpose I can take, you see from here, this is the command. Transpose of A. You see that is become the transpose of A. Okay, so what I'm going to do is that I will write transpose of A, and I need to multiply by A. And I just call this matrix as A new. I just call this matrix A new. So this is the matrix I got. And I know that it was 2 by 2 matrix. So this is the matrix I got. And if you see from here, this matrix is symmetric matrix. 17.77 is coming on the off diagonal elements. And you see its rank will be 2. Find out the A new. Its rank is 2. So it is invertible matrix. So now I go to the matrix A new, and B is already given to me. So I will find the value of now A naught and A1. So that value I will find, like I will just write solution of this system. So I will just write A new, and this is the command in the MATLAB backslash, and I will call it B, and that is just a minute. This is the backslash, or maybe just take what I will take. Okay, so I will find out the solution is equal to, okay, I can also take the inverse of A new, and then I can just multiply by B. What is happening? Okay, okay. Okay, so this B basically, you see from here, what is the dimension of B? Okay, so B is must be of the same dimension. Okay. Oh. See, we forget to multiply by A transpose to B also. So now I write B new. That's why it was not coming. B new is, again, I need to multiply by A transpose to the right hand side also. So I will take transpose of A multiply by B. And that is my right hand side. Now it is 2 by 2, 2 cross 1. So now I get my solution. So my solution will be A new, and I just taking backslash and with the B new. And that is my solution. Okay. So it means my coefficient A0 is 0.5737 and my coefficient A1 is 0.4405. And if I want to plot this one, so my one plot was already there. Now I take just one command is there. Hold on. So hold on means it will hold the same plot. Now I will write plot my x corresponding to, now my A naught is, so solution of 1 is my A naught plus solution of 2 is my A1. Okay, and then I multiply by x. So that is my this one, and I show this by a, maybe I will write the red line with this one, and that is my command. And let's see this one. So now you can see from here, this is the line I got. Are you able to see this?
Yes, sir.
Yeah, so this is my line fit. For the given data, this is my line fit. Now you can see from here, this line is passing through not a single point, not passing through any of the data point. You can see from here. The data points are this one, and I just taken this point here on the line. So this line is the best fit, but still not passing through any of the point. So that is the amazing thing about the least square method. Okay, so this is the least square method way. Now what I do is that I will hold on this curve, and now I will try to use the inbuilt function. Whatever we have done is okay, but I want to see, okay, let's see that whether this inbuilt function is already, whatever they have done here is working for this given data or not. So if you remember, in this case, I need to put polyfit. So let's write P. I write a capital P is equal to polyfit. So this is the given command polyfit, and I'm using this for X and Y, and I'm putting 1 here because I need a linear fit. See, you get the same value 0.405 and 0.5737. You can see this was my solution. Only thing is that in the polynomial, I showed you that the first coefficient, this is the coefficient of x, and this 0.57 is the coefficient that is constant value, and this is this value. So this is my P, polynomial fit, right? And now again you can plot this one. So I will write plot x, and then you can write the same thing again, no problem. Maybe I will use the same terminology again. So I will write P1. So P1 is 0.4 multiply by x, and then plus P2, that is my A, and then I will just write, with blue color, do with, let's hide this one, so that you will be able to see this also. Let's see. This is there. So now you can see it is just coming on the red line. So the same line fit I am able to find with the help of inbuilt function or with the help of the mathematics we have done using the normal equation and finding the solution. So this is the way we can find out. Now what I do is that now I will use the same way and let's try to find out, okay, approximate this with the quadratic fit. So I will use the same thing. I will just write quadratic means Q, I will write, and then I will write polyfit with my X and Y, and then I take 2. Let's see. So this is, see, 3 coefficients coming here. So this is the coefficient of X square, this is the coefficient of X, and this is the coefficient of constant. Now this is the quadratic fit. Now I'll plot, I will use the plot X, and then I will write my Q1 multiplied by X square. So X is a vector, so I have to write here X. So X, I can, this one, plus Q2 star X plus Q3. So this is my quadratic polynomial, and I will use this as, maybe I will write black with line. Let's do this one. And let's see. Yeah. So this is my quadratic fit, the black curve passing through this point. I can just remove these values. See, now you can see. This line was the linear fit, and this is the quadratic fit. So this quadratic fit is also not passing through any point, but it is the quadratic fit, giving the minimum error. The same thing we can do with the help of, maybe I will take the cubic fit. Now I will use this as a C. So C means I'm now using the cubic fit. So that is the cubic fit basically, and it gives you the value because here the data points is less. So that's why now it is not giving you much values, but now I can use this. So in the, instead of C1, and that is, I can use dot Q, then C2 is square, and then C3 is X plus C4. Okay, and then I can use here at red line. Let's see what is going to happen now. So now I am approximating the same curve with a cubic. So this is a cubic. One is the line curve, linear, then one is quadratic, and one is cubic. So this way we can approximate the given data points with a different type of approximation, and that is the part of the least square method. So this is the polynomial fit you can use for finding the values of the coefficients. Basically, whatever the coefficient you are taking, you can taking this polyfit and then you can use, and you can, so based on these values you can define different type of data. You can have a big data also. I just taken the data with 6 points so that it will be clear to you that how we are doing. But then you can choose large number of data point, no problem. In that case, maybe you can choose, just I'll show you any other function I can take. I can write here, so I can remove this figure, so this one, and write CLC clear. So this will clear the memory, and then I can use the x is equal to maybe linspace. So this is the linspace taking from 0 to maybe 1 with maybe 10 points. So this is the value of x. So this is a 10 point I'm taking. Okay. Now, based on these 10 points, I can take y is equal to, suppose I just take the points. I just take x square plus 2.3. 0. This I am just taking y. I don't know what is this. I just taken y. So this y is given to me. Now I want to take the linear fit. So what I do is that I will just take the p. So that p is polyfit. I just take for the x, y, and maybe I'll take 1. So this is my p. So p is this one. So you can see that a0 is 1 and a1 is this value. Sorry, a1 is 1 and a0 is this, because it is a polynomial fit. Now if you plot, so if I plot the x, and then I'm taking the value of e1 multiplied by x plus 2. Okay, and then I will use this as, maybe I will just take my a line, this one, that is the plot. So this is the line basically. Okay, I have not to use this one, just wait. I will also plot the curve. So I will write, hold on, then I will write plot with blue color. I will write, this is what I am doing is, so this is my data points, and I have approximated with the line. Now you can see it is going close to all these points, because this line fit is the line which is going close to all these points. You cannot get a line which is close, such a close as this value is. So that's why it is called the best line fit. Now using this data, now I will apply the same again, and instead of polyfit, I will generate the quadratic, because you see that I have generated this data by taking the square values. So it is all approximately a quadratic, and you will see that this is coming the same value. So see, now it is coming 10.3. You will see from here it is coming very close to this value, almost same value. Now if I plot this here, and I will write here Q1 multiply by x square, okay, and then plus Q2 multiply by x plus Q3 this one. I will write with the red, and then so if I put the red, go by maybe star. This one. See, so if you see this red line, it is passing through all these points because I have calculated the value of y by taking the x square plus 0.3. So if you see from here, now the quadratic equation is passing through all these points. So no problem. Everything looks fine, and it gives you the best fit. So in this case, the line was the best fit, but it was not passing through any point. But the quadratic is best fit and is passing through all these points because we have generated the data taking the quadratic function. You can maybe take this data. Again, I can here and let's see. I can close this. Now I can choose x, same x, but y I choose as exponential. Let's see. Now it is exponential function. Now if you see from here, just try to plot its value. So this is the exponential function, the data points. Now using this data point, side, so, and now I just take first I take the linear fit. So this is the value it's coming now. And this value is coming, and I use this. See from here, this is the linear fit, black color. So it is the line not passing through any points, almost. One point is there, but it is close to all this point. And now I will use, because once you write all the commands on the MATLAB, then you can just take the help of the keys up and down just to get the previous commands we have used. So this is the Q I have taken. Now it is quadratic. And this is, I'm plotting again. So you see from here, this is my curve. So I have taken the curve that was the exponential, but now we are able to capture this exponential with the quadratic fit, because exponential function is just ex is equal to 1 plus x square. So if you see from here, the coefficient of x square is 0.8, coefficient of x is 0.8, and constant is 1. So it is basically approximated by 1 plus 0.8x plus 0.8x square. That's why it is coming close to these points. Okay. So now, just here I showed you that how you can start doing these things with the MATLAB. Now you can take different data set and you can plot and you can see that how it gives the best fit for your own data. You can now discuss these things with your own data. So I think now I should stop here and I can start taking the questions. If you have any doubt, then please let me know.
Thank you, Dr. Agarwal. If there is any question from the participants, either they can raise hand or they can type their questions in the chat box.
Some questions are from Deepika Kumari.
Yeah.
So I think she was asking regarding to the graph y coordinate. I think please repeat your question, Deepika.
I guess nobody is having any question. So
Yeah.
Okay,
we
no
should
question.
the session.
Okay, if you have any doubt, then you can ask me through email also. And I will share these slides to you. So I will give these slides to Dr. Jain Mohammed or maybe the coordinator, Danish.
Yes.
Yeah.
Yes.
So
Yes,
you
there
can
is one
share.
question. There is one question.
Yeah.
Yes, you can ask your question, Sonali Bhatnagar.
Sir, I wanted to know that these fittings that we have done, this is error curve fittings, and we have done them for polynomial, quadratic, and can in nuclear physics where we get the data, it is explicitly very scattered. Like even if we take muon detectors and we take our data, we get a very random and a scattered one. So then applying this kind of a technique there, I did not get very much good results, because we couldn't fit it to a polynomial. Even I think we went up till order 3.
Okay. Yeah. So I told you that as you are saying that your data is very sparse. It is random data.
First.
Yeah. So see what is there, and your data might be very big.
Very huge, large number, because we take at least 2 sets of readings for the same voltage for the same detector in a day, and there are eight detectors. So for a month we have huge amount of data.
Yeah. So in that case, see what you minimum can do with your data, because you have the data and somebody asks you to analyze this data, then definitely you need a function, right? So this is the things you can start with, that okay, you have the data, then you try to put the best fit line for this data, right? So because this is the best fit line, it is coming from the minimizing the error. Okay.
Yes, sir, that is very clear. But what I wanted to know was, then we should go for polynomial, because
you can go for polynomial. Yeah. Even you can go for exponential also, or log function also.
Gaussian.
Yeah. I just told you that how you can do this one. That is already
yes, sir.
inbuilt.
I followed you. Absolutely, I followed you, and I think we'll try that then. It's a Gaussian fit.
Yeah, Gaussian.
Fine. Okay. Thank you so much.
Yeah. Okay.
So thank you, Dr. Agarwal, for delivering a very wonderful and thorough lecture on the applications of MATLAB, and he has given us very wonderful examples for using the least square method for data science over here. So I hope that our participants will be well benefited from this lecture.